So with our sampling distribution of proportions, how the problems will start is you'll be given some population proportion. It's the idea that we want to think about how do samples behave if we expect that proportion, but we're taking a certain sample size. So with that, as we saw from the simulation, we want to get the bell-shaped curve out. Even though we saw how a skewed distribution could come through, we're going to use the central limit theorem to help us check against that. And then what we want to see is this distribution for how sample proportions behave. So what we saw is that the center lined up with our population proportion. So that's this first piece right here, is that average of the sample proportions is just equal to the population proportion. So what we're going to end up with, if we check that central limit theorem, so our first step is to check the central limit theorem. Our next step is going to get the parameters and define our model. So we'll have a normal distribution, and the center of that normal distribution is just our population proportion. The spread of that distribution, so our standard deviation, so we're looking at the standard deviation of sample proportions, and that'll be a calculation. So the calculation is going to be this on the right-hand side. We're going to take this big square root. In the numerator, we're going to multiply p and q. Again, q is just 1 minus p. So p times 1 minus p, and then divided by sample size. And that number will give us our standard deviation. And then once we have that, then we can go to our bell-shaped curve and start answering questions in terms of probabilities and percentiles, all those things we're used to. All right, our central limit theorem. It's going to look very similar to what we did for sampling distribution of means. So we're going to check for independence, we're going to check for randomization, and the new one is success failure, which is similar to a sample size condition, but it's that we need at least 10 successes. So you'll take n times p, that should be more than or equal to 10, and then we should have at least 10 failures as well. Taking n times q should also be more than or equal to 10. So let's look at an example here, and then in the next video I'll have another example to go through with you. So the key is, if we're mapping sample proportions, again, these are types of percentages, and what can help is when you think about proportions, you're thinking about percent of a sample size. So I'll emphasize this when we get to wording our answers, because we're going to have these kind of few different types of percentages floating around. We have probabilities coming in as a percentage, but proportions are specifically a percent of n. Like the proportion of people with blue eyes, it would be 31% of 100 people have blue eyes, or something like that. So it would be a proportion coming from a sample of a certain size. Okay, so suppose 60% of all college students are either very satisfied or completely satisfied with their online shopping experience. So we have the 60% coming through. So it's 60% of a group. In fact, it's the percentage of all of this group. This right here is your population proportion. So they're giving us this population proportion of 60%. We decided to take a nationwide random sample of 2,500 college students. So we're going to take a sample. The idea being, when we take this sample, we expect that 60% to come through. However, with random variation, maybe we get a little bit more. Maybe we get a little bit less. Maybe we get an outlier and something really strange happens. It can all be a possibility. Is it reasonable to use the normal model for the sampling distribution of the sample proportion? Alright, to know whether or not we can use our normal model, that's where we check the central limit theorem. So what we're going to do is check independence, randomization, and success failure. So, again, we have to do this even though they prompted here with your homework and on an exam. If I don't prompt you, you still have to do this, and that the central limit theorem is crucial to basically proving that we do have a bell-shaped curve. So independence and randomization, just assume we're good there. Independence would be the fact that how these random college students answer the survey would be independent of each other. You could also talk about how 2,500 college students is probably less than 10% of all college students. Things like that would give us independence. Randomization is actually clear here because they tell us that we have a random sample, so that's all good. Success failure is where we need to show a little work. So what we're going to do is take 2,500 times 0.6, so that'll be our n times p. Then we need n times q, which if you have a p of 0.6, q is just 1 minus 0.6, so that'll be 0.4. So we also need to show that 2,500 times 0.4 is also large enough. So 2,500 times 0.6 is 1,500. 2,500 times 0.4 is 1,000. And both of those are more than or equal to 10. So as soon as we show those are large enough, we pass the success failure condition. So with that, we now know that we have a normal distribution. Yes. Find the mean and standard deviation of the proportion of survey response. So the wording here, mean of the proportion and standard deviation of the proportion, that's describing that notation up above there for mean of the proportion, standard deviation of the proportion. So, mean of the proportion, just copy the population proportion. So that's going to be 0.6. So middle of our distribution should line up with the true population proportion. Standard deviation we need to calculate. So we're going to take square root p times q over n. And from there, let's go ahead to a calculator so I can show you how to plug that in. The key mistake here can be plugging in the values incorrectly and getting the wrong standard deviation out. So with this, we want a big square root. So outside of everything, we want this square root. Under that square root, we want this fraction. So what I did is I hit the square root button, and now I'm going to put my fraction. And just make sure that the entire fraction is under that square root symbol. The common mistake is to only have it in the numerator or only have it in the denominator, but it should cover everything. So in the numerator, we're going to multiply 0.6 times 0.4, and then the denominator, we're going to have 2,500. And that'll give us the standard deviation of 0.0098. So with that, we're going to have this normal distribution centered at 0.6, standard deviation of 0.0098. Something to keep in mind here, again, these proportions, it's all in terms of percentages. So the number line that we're working with is going to be decimals between 0 and 1. So with that, it operates a lot differently than our sampling distribution of means, when you could really have any sort of whole number coming out. It could spread very far. We're really restricted with our sampling distribution of proportions. So a question I often get from students is that it can be kind of, I don't know if unsettling is the right word, but it could be concerning getting such a small standard deviation out. What you could think of is that really this is in terms of 60%, and this is like almost 1%. So in a scale of percentages that's about right, it's that the numbers can just look so small here, and it's because they're in the decimal form of percentages. with that, it's good to keep in mind that that could suggest a miscalculation too. If you get a large standard deviation, like if I got anything over a whole number here for the standard deviation, when I'm dealing with proportions, that's most likely incorrect, because when we start making our number line for the graph, those numbers have to be between 0 and 1 for the percentages. So just keep in mind, with proportions, we're working with percentages. So here's an example of a type of question that we could ask for a sampling distribution of proportions. So we're looking for a probability, and it's asking for the probability of the behavior of a sample proportion from a sample size. So we have a sample size, and they're asking how p hat behaves with that sample size, and we want to see what's the probability that that proportion is at least 57%. So in this section, what you're going to be looking at is this probability of a percentage occurring. That's going to be this sampling distribution of proportions coming through. So what this will look like is we'll have our bell-shaped curve. We expect 0.6 to come through. And just to give you an idea of a number line, I'm just going to round a little bit. I'm going to go with that rounding of 0.01 for the standard deviation. Like this would be a 0.61, this would be a 0.62, 0.59, 0.58. So this is what I was talking about in terms of our number line, is that we're seeing these percentages coming out. It's that if I take a sample of 2,500 college students, we could see values from 58% to 62% are pretty likely. Anything outside of that's kind of unusual. And for our example, we're looking for the probability of at least 57%, which is the equivalent of 0.57. So what I'm doing is, I'm out here actually, way out in this tail, looking at 0.57, and then we want the probability of at least that. So I want the probability of being there or larger. So we should get a very large probability out because there's a high likelihood of that occurring. I'm just going to shade that in roughly. Alright, so I need that big area to come through. So we're looking for the probability of a random variable being more than or equal to 0.57. So let's go to GeoGebra and set this up. So mean is 0.6, standard deviation is 0.0098. Here's that little trick that I was talking about in the previous video. I'm trying to type 8 right now and it's not letting me. But if I backspace back to that decimal place and then go 0098, it works. I held my breath there a little bit, making sure it would work, because sometimes this does this, sometimes it doesn't. I believe this comes up a lot with these sampling distribution of proportions because of the small values. So again, if you can't type in that last digit, it is important to have those 4 decimal places because it can change the answer sometimes. So just backspace back to your decimal that you typed in there, and then write it out again. Okay, and then I want area to the right, and I want that area to start at 0.57. And that's at 0.9989, which makes sense. Very large probability of landing in that region there. So, we get our answer out. Now, this is where I want to emphasize we have these different percentages floating around. Making our sentence, we want to be careful of how these percentages relate. So the types of percentages that we're looking at, like this 0.9989, that's a percentage, but this relates to percent chance or percent probability. So that's our actual probability, that's our solution. This 0.57 is referring to the percentage of the college students. That's the percentage of our sample size. We're saying 57 or rather at least 57% of the 2,500 college students agree or say that they enjoyed their online shopping experience. So that's where we have these different percentages, and it's important to keep them clear. Probabilities coming through on that right-hand side of the equation in GeoGebra. So for a sentence, I typically start out with just stating what the probability is. So I'm going to say there is a 99.89% chance. And when in doubt, just go back to the wording of the question, because that'll usually give you a structure to follow. I would say something along the lines of, there is a 99.89% chance that at least 57% of the 2,500 college students agree. So, in the answers here, you're going to have two percentages showing up, but the idea is that one's a probability, so percent chance or percent probability, and then the other's coming from the wording of the question, of that 57% that they wanted us to have as the cutoff value. Alright, so that's one example. In the next video, I'll go through another example.